So I'll speak today about Mpemba effect, and this is work on granular physics, and this one I've done with my collaborators. Arnab is here. Apurva is my student who is right now a postdoc in Bordeaux. And today's work will be based on these two papers. So I take two water in a beaker at two different temperatures, say one at 30 degree, one at 50, and then you put in a freezer and you ask which system will cool faster. So the result of this is the Mpemba effect. So the conventional answer is if your temperature difference between the final quench temperature and the current temperature is small, then the rate of cooling is governed by the Newton's law of cooling. It says that the rate of change of temperature is proportional to the difference in temperature with the environment. And then there's an exponential decay. But if you put some condition that when I reach close to epsilon, that is my time of equilibration, then it's straightforward to see that the time to equilibrate increases with the initial difference in temperature. So hotter time takes more time to equilibrate when you quench it. So what is Mpemba effect? So in an experiment I described in the first slide, you actually do the experiment. You measure the time to start freezing, and this is the initial temperature from which you're putting in the fridge. Okay? And then this curve is non-monotonic. The hotter system, which is closer to 100 degrees, freezes faster. So this anomalous effect is called Mpemba effect after he and Osborne wrote a paper on this topic. No, Abhishek keeps telling me it doesn't work, but okay, so it does not work. But then, let's take another experiment, which is not done by Mpemba. But so later, many more experiments come about to ask what is the reason for this effect in water. So for example, this paper does show Mpemba effect because this is the time taken for freezing, and this is the initial temperature, and it is decreasing with temperature. And here they say that, if you take water with dissolved gases, then the effect is there. But if you remove all the gases, then it's not there. But that's not the only reason people suggest, there is some other effect in some other experiments where they show the Mpemba effect and they give a different reason. Now we are not, so the point is that, the effect is robust, and there are few papers which say that the effect doesn't exist. But we are not going to talk about water. The initial the excitement was about water, but that is not what I'll talk about. So let's ask about Mpemba effect in a more general scenario, not water. So you have some final temperature or final, some other, you have a system with a final steady state. That's after you quench, this is the final steady state. And there is an initial hot state and a warm state. And the hot state is further away from the final state, and the warm state is intermediate. Now we quench by changing some parameter like temperature or something, and you ask which system equilibrates faster. So to quantify this, you will need some distance measure. No? You want to ask, given a particular state, how far is it from the final steady state? So I'll call this D star. And then you ask, if I plot this distance measure as a function of time, do these two curves cross? So if the hotter system is further away, does it become closer than the initially cooler system? Now, this slide, there are quite a few experiments, but the point of this slide is to show that it is not water alone. There are many other systems which show Mpemba effect. So in all of them, there is some y-axis, and there's a time along the x-axis, something along the y-axis and here. What is along the y-axis is like the distance, a proxy for the distance. So for example, in this example is magnetization. Here it is some excitation energy, and here it is some other proxy distance. And the claim is that as time goes on, there is crossing of curves. So the hotter thing, what I call hotter, becomes equilibrates faster. So let me summarize. So the Mpemba effect is generic. It is not seen in water alone. So then how does one understand? So the other limit is look at simple models. So there was a paper in 2017 which made this effect very popular in the last, this paper sort of triggered a lot of papers on this effect. So let me summarize in one slide what their idea was. So they looked at a three-state Markov process. Oh, no. So let me start with the curve on the top. So they imagined that suppose you have some potential with multiple minima. So, and you have some system evolving in this potential. So to model that, they made a three-state Markov process, which 1, 2, and 3 correspond to the minimum of these potentials. And there is some rate of going from 1 to 2, 2 to 3, and 3 to 1. That rate obeys detailed balance, but it is activated dynamics because there's a barrier to cross every time you go. Now, in this particular model, they showed that if you follow the protocol I told before, there's a final temperature bath. There are two initial hot temperature, which is, and they define let's say, suitable distance measure. Then the hotter object, which is given by the red, and the cooler thing, the cooler object equilibrates slower. Okay? So they could show Mpemba effect in a very simple three-state model, no complication of water or something like that. So in this case, the hotter cooling would be E3 to E1? No. How does it, because in equilibrium, you can be any of the three states with some probability. But how does it reach that equilibrium probability? That is the distance measure they look. No, you start with the equilibrium measure, then there's a final equilibrium measure. How does it decay from one to another? So the explanation, I have made a small figure to explain what the idea was. So suppose I have a double well potential. And so there's one single particle moving in this double well potential. It can make transitions from here to here and backwards. And now the rate of going from crossing this barrier is proportional to the barrier height, e to the power minus delta u, to go like this. Now, so let's say the final bath temperature is where it occupies mostly this minimum. Now I have two temperatures, the initial cold temperature and initial warm temperature. So if in the initial cold temperature is the mean KT, I don't know, KTU corresponds to somewhere below this barrier, then when I lower the temperature further, it has to make this transition from here to here, which is activated. While at the initial hot temperature, the rough energy is roughly here, then it can just move without having to cross a barrier. So that is the explanation. Okay, so this is a very nice, plausible explanation, which is appealing. In fact, this was implemented in an experiment on a single colloidal particle trapped in a double well anharmonic potential. Okay? So in this paper, they looked at this problem, and so it's one Brownian particle, asymmetric double well, quadratic, and it is trapped at the boundary. And what they do is they do the same procedure. They do two quenches, one from a hot temperature and one from a warm temperature into a cold temperature. Now, you can ask, how to do a quench in an experiment? So what they do is, you have the potential is given. So if I ask, what's the probability of finding a particle somewhere here? It is e to the power minus beta u. Now in the experiment, they start with, let's say, 10,000 realizations they do. So in each of the realization, what is the x they choose? They choose from the Boltzmann distribution corresponding to that temperature. So they can mimic the initial condition from that thing. And then the optical, the trap is always maintained at the final bath temperature. So the quench is perfect. So what they plot is they track the trajectory of the particle for these 10,000 trajectories and then make the distribution. What's the probability of finding a particle at point x at time t? So this is here, this is the final bath temperature, and you can see the distribution does not change with time because they're already equilibrated. Now, if I take the hot one, it was initially flat because the temperature is very high, but in a very short time, this one looks like this. But if I take a warm one, the intermediate temperature, the distribution takes a bit of time to reach. So you can, from the distribution itself, you can read, from these figures, you can read out experimentally that the warm one takes more time to equilibrate than the hot one. Okay, is it clear? Now, so now what do they do? So what they measure experimentally is this P of xt, the probability the particle is at point x at time t. What you know from Boltzmann distribution is the final steady state, final equilibrium steady state. So you can take this difference, integrate over dx, and say that is my distance measure. And this you can plot from the experiment, and you find that the hot object reaches to 0 faster than the warm one. So this is Mpemba effect in an experiment on a single particle. There's no need for interaction and a very simple potential too. And they also demonstrated something called strong Mpemba effect, in which if you plot on a log scale, so you plot this distance on a log scale, you can see that the decay itself is exponentially faster for a hotter system as compared to a cooler system. So the previous one need not be exponentially fast. They could be the same rate, but different times. So now let me spend a couple of slides. How can we define Mpemba effect unambiguously? So let's say you have a Markov process. So that Markov process is defined by some transition matrix W. P is my row vector or column vector of all the probabilities. And if I, given a transition matrix, if I evolve the system in time, at long enough times, the system reaches a steady state, which is time independent, with a coefficient which is exactly 1 for whatever steady state to start with. Then there are corrections given by, the first correction depends on the first excited state of W, then the second depends on the lambda 3, lambda 4, and so on. Okay, so I've written up to the first one. And so in the long time limit, you have the steady state. Now, this lambda 2 is just the eigenvalue of lambda W. It cannot depend on the initial condition. It's only a function of the rates. So only place where the initial condition comes in is this coefficient A2, which is obtained by the inner product of the, if you take the left eigenvector of the first excited state with the original state, that determines A2. Okay, so and then there's A3, A4, A5, and so on. But those are not, for the large time behavior, only A2 is important. A2 corresponds to the coefficient of the first excited state of this W. Okay, how would quench 2?
Rajesh, sorry, just a very basic question.
Yeah.
So, if you can have some very strange initial conditions which might affect the rates, right? Maybe I'm getting confused about. So why do you? So at some given temperature, you can have some very weird initial condition that doesn't cool down or something. I mean,
No, so that comes with the probability.
right. So why is that very? So that's very low probability. Is it such strange initial conditions?
So like in a Markov process, whatever initial condition you start with, you will equilibrate in the end, unless if it is ergodic.
With the same rate. So the rate really doesn't depend on the initial condition.
The lambda 2.
Lambda 2.
Lambda 2 will not depend on the initial condition. Lambda 2 is just you diagonalize W and you take the first, the largest eigenvalue is 0. The next one is lambda 2. But the example in Deepak's talk, he was trying to point out that from this spectral thing, it was not working out well. But forget about that. This is true otherwise. So now you take two systems, one at high temperature TH, one at cool temperature TC, and you're going to quench it like before. So now, I have just rewritten the equation here again. Now you're going to look at the distance measure, which is the distance between the current distribution with the steady state. And in the long time behavior, it is only one term that is coming. Okay. So when I now plot D as a function of time, in the long time behavior, the curve that is below is the one with the smallest A2. So whatever initial condition had smaller A2 will be closer to equilibrium than the one with larger A2. This is the point. Now you have to ask, at time t equal to 0, what is larger? Is it the higher temperature, lower temperature? And for equilibrium systems, you can easily show that the higher the temperature, the further you are from the equilibrium. So if I start with a higher temperature, the distance measure is higher, and if it happen to have a smaller A2, there'll be a crossing. Okay, so that is the point. So if now I managed to create a system where the A2 was lower for the hotter temperature, then Mpemba effect will be present. So just to summarize now, what is the protocol to follow with A2? So we again remember A2 is only a function of initial temperature. So I can calculate A2 given the final bath temperature TB. Then I ask, is it non-monotonic? So if I have a curve like this as a function of time, then I say, oh, I will choose my high temperature to be this one and low temperature to be the intermediate temperature TC to be here. Then I'm guaranteed that the A2 is smaller for the hotter temperature, and I'm guaranteed Mpemba effect. On the other hand, if A2 is non-monotonic, then Mpemba effect is absent. Okay, so for a Markov process, now we have reduced the presence and absence of Mpemba effect to calculating this coefficient A2. Now, in the strong Mpemba effect, so this is, I keep one more term here, and if I happen to choose a temperature for which A2 was exactly 0, then the hotter system cools exponentially faster. Okay, I have 8 minutes. So let me summarize. So you give a Markov process, you compute A2 and look for non-monotonicity for Mpemba effect, look for zeros for strong Mpemba effect. Now with this background, now I'll ask a particular question and give the answer. I have 8 minutes left. So what is the explanation for Mpemba effect? Is it metastability? There are some other reasons that we also suggested, but turns out may not be the correct one. But the metastability was the one I argued in the beginning, and it seemed quite appealing. So I'll ask whether, is this the correct explanation is my question. And then if I get a little bit of time, I'll summarize what is the role of activity and what is the role of rate of cooling when you don't do an instantaneous quench. So the problem I'll consider is a colloidal particle or a Brownian particle in a single well potential. And it happens to be linear. Why linear? Because when you put a linear well, it's solvable. Okay? And the other motivation is that this particular potential is also experimentally realizable. Now, if I can demonstrate Mpemba effect in this problem, then it means that metastability is not required. There's no double well required, and that cannot be the right reason. Okay, so that is. Okay. So one slide on how for this audience is not required. So you have a Brownian particle. You study. You start with the overdamped Langevin equation. You write the corresponding Fokker-Planck equation in this potential, and then you can solve for the various the eigenspectrum for this operator in this potential. Okay. And then given that given this potential, you can ask what is the value of A2 for a given potential, and that is what we do. Okay, so recall the criteria. Again, one more time, I remind you about the protocol. So if I compute A2 for a given potential and A2 is non-monotonic, then I'll say Mpemba effect is present. Otherwise, I'll say it is absent. Okay, so now to show that metastability is not necessary, I have to just give one example where Mpemba effect is present. So I consider two potentials. One is the red one, and the other is where it's red followed by the blue. So this line is the calculation of A2 with temperature. A2 for the blue potential is like this, and for the red one, there is a minimum, and therefore Mpemba effect is present. And to give a even more direct evidence, if I look at the distance measure, then it shows a crossing. So similarly, you can ask for inverse Mpemba effect. You can ask, if I cool the system from two different temperatures, does it have anomalous heating? And that also you can explicitly show for this particular single well potential. So now, so I showed one particular instance of existence of Mpemba effect without any double well in the thing. So then it's immediately the question comes: did I choose something very fine-tune something, or is it a generic phenomena? So, this is the potential. These are all non-dimensionalized values. There were three parameters. One is where does it hit here? Where does it hit here? UR, UL, and where does the center come? Is it here? Determined by some value alpha. And we make some phase diagram. The three parameters. So we fix one parameter alpha, then ask which regions have Mpemba effect. Then I change alpha and do the same phase diagram and so on. And clearly, about 50% of the phase diagram, you can get Mpemba effect. So it is very generic. I don't have to particularly choose one fine point to see whether Mpemba effect is present or not. Okay, so I have 4 more minutes and lunch is also there. I can choose to tell about this. So let me just flash some slides and I'll go to the conclusion. So the same analysis can be done for an active Brownian particle. Now the equations become a bit more complicated because there is one more term which is the self-propelling term that makes it, then you have to worry about are they moving left, are they moving right, and then you can do the same analysis. The thing is that we cannot find a pattern. Activity can sometimes reduce Mpemba effect, activity can sometimes increase Mpemba effect. I will just I'll not talk more about Mpemba effect in this. No, activity. So let me summarize. So Mpemba effect is a counterintuitive phenomena in systems relaxed into equilibrium where something that is far away equilibrates faster. So now I would like to propose that, if you want to understand this, you must study a single well potential as the minimal model for studying this problem, rather than studying a double well or more than that. This is sort of the minimal model to study. And metastability has been an appealing and plausible explanation, but it is not a necessary requirement. In fact, if I were to really believe that argument, then the inverse Mpemba effect does not work. Okay, so that is the point. And okay, so some of the outlooks. So the first, actually, it's quite disappointing that you could find a Mpemba effect in a single well. Reason being, now you are saying that the effect seems to be in some detail of the initial states. Okay? But we have been trying to analyze it a bit better in terms of entropy production, work extracted, etc. But we have not made much progress. The other is, the quenching is infinite cooling. Then the Newton's law is very slow cooling. How does it, can you extrapolate, can you interpolate between these two? So we have been looking at that problem too. So some other things are quite, I find counterintuitive. For example, if I reduce my initial temperature, where the red is the temperature, how it decreases with for the hot system, and so there's next decay, which I say the temperature of the system decays exponentially. So in this system, always the temperature of the hotter system is higher than the coolest, the bath of the bath. But the hotter system equilibrates faster. Okay? So this is quite counterintuitive. Similarly, for other cooling laws where the temperature of the hotter system I maintain always higher, but it cools faster. Finally, a couple of problems which we were just for as an outlook. So the strong Mpemba effect can give a pathway for faster cooling. So you can ask, I can heat first to a certain temperature and then cool. But then, you can ask, that may be faster, but there's a thermodynamic cost for this. Can you do a thermodynamic analysis for such protocols people suggest? And finally, what is the particular reason for water? So that is also an open. Thank you.
Okay. So for that double well potential, there was a simple intuitive way that in one case there was a barrier crossing, in the other case not. And in your case, the difference seems to be when the asymmetry is more, you have the Mpemba effect, when the asymmetry is less. So is that the intuitive understanding?
But
That
too much asymmetry also does not help.
it does not help. There is a reentrance.
Yeah. So there is no, so the plots are just data put, there's no explanation. I have no explanation as such.
I mean, that would be nice to some
Yeah.
intuitive sort of thing that, is there any other measure that is,
Yeah, so
undergoing?
that's what I've said. Maybe one should analyze in terms of more, not in terms of A2, but in terms of some, how much work is extracted if you start from a quench like that or something like that. I don't know. We are trying some.
So, I mean, it seems to me like for water, I mean, if it's there, then it should be for very different here, right? Because it's more like a macroscopic system, while for small systems where noise and all is important, but for water, also when you put water in, it's a different temperature, like the inside is still at very hot, there's conduction, and so it's a more macroscopic phenomena, right? So the explanation has to be completely different.
Yes, and or not just that, when you do an experiment of freezing, so you're quenching across a phase transition line. Now, those data, how do you know it has frozen? Meaning that that part of the experiment, I'm not very sure. So there's a lot of ambiguity there, that part also. But as I said, I don't know whether people have suggested multiple reasons for that, hydrogen bonding, this, that, and each one of them, they have evidence for that. So, but I'm saying that from the analysis of simple models, it seems that this effect is generic. That is the thing. It is not surprising.
Deepak?
Yeah, so my question is similar to what Abhishek asked. Suppose you take an n particle system, then generally the W matrix is exponential in n, and A2 will be exponential in minus n. In which case, the answer should not depend too much on a particular coefficient A2, but a weighted sum of all different values of A.
No, so there is but a very long time limit.
That is the Poincare time.
No, okay. So firstly, so suppose we did analyze some larger systems. So the point is that, the calculation of A2 is not, that's a theoretical one. Practically, it's not possible. So practically, when you do, you have to use some other proxy, like effective temperature or effective magnetization and so on. But when you do that, then what we find is that sometimes the definitions are not, the definition of the effect is not unambiguous. In one variable you find, in another variable you do not find. So I'm answering a different question, but I'm saying that for infinite system, what is easy to measure is something else, which you have to do carefully.
Okay, thank you.
More questions? No, in that case, let's just thank Erna, Manon, Raul and Rajesh for this nice session of talks.